So, we were talking earlier about the effects of silica fume on hardened concrete, and as we had discussed, primarily the effect will be on enhancing the hardened properties of concrete, primarily the strength and modulus of elasticity, because the fine particles of silica fume are able to densify the interfacial transition zone, and that helps in further reducing the extent of penetrability of the concrete and also adds to the stiffness of the material. Now, there are specific instances of the contribution of silica fume to the volume of the paste, which may lead to some different conclusions with respect to the tendency to creep or shrink, but the increased resistance to deformation caused by the higher stiffness when silica fume is used as cement replacement may tend to overcome those effects. Okay. One important aspect, obviously, like any other mineral additive, the expansions due to alkali silica reaction are reduced when silica fume is used as a cement replacement. Now, just to give you some examples of research studies that have been done with silica fume, this is a study by Rosen et al. Published in 2015, where you can see clearly that in the microstructure of cement paste, when silica fume is used as a cement substitute, you can see increased densification that is actually happening. So, this is your 100% Portland cement on the top left, and this is a structure shown by backscattered scanning electron microscopy. Okay, the technique is quite similar in terms of interactions with the sample. The technique is similar to your optical microscopy, which many of you are familiar with, except that instead of light we use electrons to image the surface of an object. Now, here the denser the object, the greater will be the reflectivity of the electrons. So, the whiter phases that you see here are the denser phases, denser implying which do not have much voids in them. Okay. So, here the denser phases are the ones which are unhydrated cement grains, and the gray basically refers to all kinds of hydration products that are actually there. Your calcium hydroxide is represented by these whitish phases, whereas the CSH is the dark gray phases that you see, and also the light gray phases which are right outside the unhydrated cement grains. Okay. But what you also see is a large number of black spaces. The black spaces are the ones which offer very little reflectivity because they have least density, that is your porosity in your system. Okay. So, as you go from 100% PC to 10% silica fume to 25% silica fume and to 45% silica fume, of course, it is a totally impractical mix to do in real situations, but nevertheless, if you can produce a good mix with 45% silica fume, what you see is almost a complete elimination of the porosity in your system. Okay, because the silica fume particles have actually filled up the porosity quite nicely, and these are all at room temperature at 20 degrees Celsius after 3 days of hydration. What you also can noticeably see that the extent of calcium hydroxide is getting reduced significantly as you increase the percentage of silica fume. This is another research study which explains the reduction in alkali aggregate expansion or expansion in alkali aggregate reaction. So, as more and more silica fume is used, the expansion is falling to levels which are much lower than what can be characterized as a reactive aggregate. Okay. So, whenever you have reactive aggregate, the use of cement replacement by mineral admixtures is the first line of defense to restrict the expansion to a level which is controllable. And chloride resistance effects are usually very good. Again, why? Because we are affecting the permeability of the concrete. The concrete becomes less permeable, and that leads to a better resistance to chloride penetration. Again, the direct effect on chloride because of permeability is also the reason why silica fume concrete becomes less prone to corrosion problems. Okay. Very low permeability. So, oxygen and moisture that are required for cathodic reaction may not be able to get in easily because of the concrete being very dense and impermeable, and then because ionic transfer has to happen in the conducting medium, that is your concrete, the conductivity of concrete gets reduced significantly whenever you substitute cement by other pozzolanic materials, because you are binding the alkalis, conductivity is reducing, and because of which your ionic passage in the electrolyte or the medium surrounding the concrete or surrounding the steel is going to be restricted significantly. So, your corrosion rate also will reduce whenever any mineral admixture is used, and particularly so when a high reactivity mineral additive like silica fume is used. Now, carbonation is a tricky situation, right. We talked earlier that carbonation happens when CO2 enters concrete from external environment and interacts with calcium bearing phases to convert those to calcium carbonate. The problem with carbonation is not the chemical reaction, the problem is the fact that this reaction lowers the pH, and that lowering of the pH makes the steel susceptible to corrosion, right. Issue is when you substitute cement with mineral additives, we know that we are converting calcium hydroxide into CSH. So, in carbonation of blended cementitious systems, you have very little calcium hydroxide available to offer some initial resistance to the passage of carbon dioxide. So, your CO2 will be able to penetrate greater depths in blended cementitious systems, irrespective of the fact that blended cements have lower permeability as compared to concrete with ordinary Portland cement, right. So, there are two effects at play here, right. One is permeability, the other is your lime content or calcium hydroxide content, right. In the case of silica fume, we use very little of it, and a lot of it may not even get a chance to react and may be simply functioning as a filler. So, silica fume, although it is highly reactive pozzolan, it is going to consume calcium hydroxide to some extent, right. In ideal situations, it may be able to consume all of calcium hydroxide, but that may not actually happen because each and every grain of silica fume may not have access to calcium hydroxide, depends on how it is spread out in the microstructure, right. So, the effect of the permeability when such small quantities of silica fume are used can be more dominant than the consumption of calcium hydroxide. When fly ash or slag is used, how much percentage are we talking about? 30 to 50%, right. We are talking about at least 30% fly ash, 50% slag. So, lot more is available in the microstructure. So, possibility of calcium hydroxide interaction and consumption is much greater in such instances, right. But it only happens over a longer period of time. Now, we talked about this earlier that when your system is lime rich, when it has more calcium hydroxide, the calcium hydroxide starts forming calcium carbonate, and that almost forms a barrier on the surface of your concrete through which CO2 cannot further penetrate easily. But whenever mineral additives are used, since calcium hydroxide is not available in large quantity, right, your CO2 is able to penetrate into the CSH or other calcium bearing compounds. CSH also will start carbonating, and carbonation of CSH leads to more porosity. So, if it leads to more porosity, obviously more CO2 also will go in. So, your penetration depths with concrete with blended cements is generally going to be more than penetration depth with OPC. But in case of silica fume concrete, there may be an exception. Okay. You may have sufficiently low permeability with silica fume concrete to avoid the effects of reduction of calcium hydroxide content. Well, it depends on a case by case basis, we need to take that, but on the whole silica fume concrete may show a lower carbonation depth. Now, in terms of abrasion and erosion resistance, silica fume performs very well. Again, why? Because it is increasing the hardness of your concrete by filling up the porosity well enough because of its extremely small particle size. Where does hardness and abrasion resistance or abrasion and erosion resistance, in what kind of structures is it important? Pavements, you need good abrasion resistance. Where else? Sorry? Underwater construction, especially sea construction. Construction for the sea, you need very good abrasion and erosion resistance. Dams, you need good resistance for spillways, not for the entire gravity dam because that is usually low grade concrete, but for the spillways you need high grades of concrete which need good abrasion resistance, right. So, in such cases silica fume can be a very good material to use. The interesting part is the fire performance of silica fume concrete is not very good. One example is a channel tunnel fire. how many of you know about the Channel Tunnel fire? This Channel Tunnel is basically the tunnel which goes from England to France in the English Channel, under the English Channel, right? And this tunnel had lining which was made with high performance concrete. The lining of the tunnel was with HPC with silica fume, high performance concrete with silica fume. So, it was a very high strength concrete that was used for the lining, and one truck which was bearing petrol caught fire inside the tunnel, and because of the sustained fire, the concrete lining made with high performance concrete completely spoiled. It completely spoiled, and there was a major repair to be done for the tunnel. Now, what could be the cause of poor fire resistance of silica fume concrete? Okay. Exactly. When concrete heats up, water will convert to steam. The steam needs to come out of the concrete, like your pressure cooker, right? The weight goes up and the pressure gets released, and that's exactly what's happening here. There's no release of pressure that's possible in concrete that is extremely dense. With concrete which has very less porosity may not have sufficient pressure to push out the water, or may not have sufficient passage to push out the water or the steam. Because of the pressure that's getting built up, your concrete starts getting stressed and completely spoiled out, right? Later, what people talked about is, okay, you can produce high performance concrete with silica fume, but use polypropylene fibers inside. That will reduce the spalling. Why? Oops.
This type of propylene fiber, when temperature rises, then this fiber gets melted down.
Yeah.
It creates a pore.
Exactly.
Pressure will decrease.
So, at the temperatures of the fire, the polypropylene fibers start melting, and it allows allow the passage of steam to the external environment. So, polypropylene fibers as an additive to concrete used in the tunnel linings is a very popular choice these days. Okay. So, but with silica fume, we can expect that there's going to be very high pressures because of the steam generation inside the concrete. Of course, that doesn't mean we can start making concrete more porous, right? It's only in an extenuating circumstance like a fire where we put fibers inside the concrete. Right. So, most of the aspects that we discussed about resistance to chemical attack and corrosion and carbonation, a lot of that will sort of repeat in our discussion of other chemical additives or other mineral additives also. But nevertheless, we have to understand the basic chemistry of these materials as to what goes into making the system different from a plain Portland cement based mix. So, we have discussed earlier that ground granulated blast furnace slag is not really a mineral admixture, it is a hydraulic cement on its own, because it has the potential to react with water. However, it needs some activation for the reaction. It can react on its own, but it happens very slowly, but in the presence of the activators, it can actually react much faster, right. So, that is why we call it a latent hydraulic binder. Okay, in terms of cement chemistry, you may hear different terms for cement. Okay, sometimes it is called cement, but that is only when plain Portland cement is used. Sometimes we call it cementitious material, okay, and sometimes we call it binder. Okay. Mineral admixtures, they are also sometimes called supplementary cementing materials. Actually, that is the more common name these days. They are sometimes also known as extenders. SCMs, mineral admixtures, extenders, sometimes they are also called CRMs. What is CRM? Cement replacement materials. Okay. So, you have to be careful about what the authors of papers and books are referring to when they refer to all of these materials. Okay. Extenders is a term that is used in Europe for defining the properties of special cements which have more and more of these mineral additives as replacements of cement, right. So, this is something that you know very well. Slag is collected in the blast furnace process, that is why the name blast furnace also comes in the name of the slag, ground granulated blast furnace. Slag is the full name of slag. So, we know that we add limestone in the blast furnace process. Why? What does limestone do? Sorry? No, that is okay. It produces lime, but what is the function of limestone? All this can be done without limestone also. No? All you are doing is burning the iron ore or heating the iron ore at a very high temperature. No, it reduces the temperature of melting of the iron. So, it is a fluxing material. It is a fluxing material. It reduces the temperature of the melting of the iron. So, here what we are simply trying to do is melt the iron ore, okay, and iron ore melting is happening across the range of temperatures. Now, what really happens here is that the limestone is contributing your calcium oxide. It is combining with the impurities present in the iron ore, which are in the form of silica, alumina and so on, right, and gets collected as molten slag, which is lighter than molten iron. So, it is collected on a basin above the molten iron, and then it has to be cooled to produce the granulated slag. Now, molten slag of course is at very high temperatures. It can be cooled in various ways. You can cool it in air, you can cool it by throwing water on it or putting it in water completely, which is called quenching, right, or you can pelletize and then cool it slowly. So, there are different ways of cooling, but to produce a concrete or produce a material that is highly amorphous, what methodology should you choose? Cool fast or cool slow? We need to cool very fast in order to make the material amorphous. If you cool slowly, just remember same thing with your molten magma, right, which makes your rocks. Granite is intrusive igneous rock, your basalt is extrusive. All of these are forming from cooling magma. So, extrusive is above the earth's crust or outside the earth's surface, which there is air cooling happening there. So, it is relatively faster as compared to the cooling that happens under the earth's crust. So, that is why granite has a crystal size or grain size which is much larger than that of basalt, which is formed on the earth's surface, right. So, same way here, if you cool very fast, you lead to more amorphous nature. If you cool slowly, it becomes more crystalline, and in that case it will not be reactive, right. So, you have to cool fast. Generally quenching is done to get what is called the BFS clinker, okay. So, quenching or cooling by water is done to get the BFS clinker, okay, and this BFS clinker, blast furnace slag clinker, is further ground, okay. Yeah, this is the other form of slag, which is air cooled slag, okay. Air cooled slag is what would not be reactive like a blast furnace slag, a regular blast furnace slag, which is quenched, okay. So, this is out of quenching, and this is from air cooling. And air cooled slag is a material that is fairly hard and can be quite useful as an aggregate in concrete. Only problem is slag is a material that may have a large iron content, obviously from it is obtained in the process of manufacture of the iron ore, removal of iron from iron ore, and because of that it may also contain significantly high iron content. So, what will be the relative hardness of slag as compared to cement clinker or as compared to limestone? Slag will be less or more harder? More harder. It has got iron in it, it is going to be more harder. So, crushing slag into aggregate sizes from the large bulk may be quite energy intensive. Similarly, crushing slag into very small sizes to become a cementitious material is also fairly energy intensive, okay. So, granulated slag is the smaller pieces of the cement clinker or slag clinker that are obtained by quenching, and then those are ground. That is why we call it ground granulated blast furnace slag, okay, ground granulated blast furnace slag. The process of pelletization is another alternative to granulation, where the liquid slag is made to fall on a vibrating plate, okay, and this vibrating plate feeds it to a variable speed drum, and the particles of slag which are cooling because of the air interaction are thrown by this drum to different distances, okay. So, what happens is there will be some pellets that form which are larger in size, there will be some particles of slag which are smaller, which may fly further. Okay. So, you collect the granulated material over here, which is of the size of the granulated slag size. You can see about 1 to 2 centimeters is the size, and then the pellets, the small pellets are basically getting formed on the other side. So, you can then further grind this to make the reactive slag. Only thing is here, the pelletized slag may not have the same reactivity as your quenched material, okay, because air cooling is happening here. The air cooling is happening of very small specks of the liquid slag. That is why it cools much faster than the entire slag together. But in spite of all of this, there may be still enough slag available which people are not able to cool by quenching or pelletization. They may actually be cooling it by just storing it outside. Okay, they may be dumping the liquid slag outside in areas which can receive such material, where it will get slowly cooled by air, right. And these are the ones where air cooled slag can be formed, air cooled blast furnace slag, ACBFS. Why do we keep bringing the name blast furnace inside? Because there are other furnaces also, there are other types of furnaces in steel manufacture also, like the electric arc furnace, there is also an LD furnace. All kinds of slags can be actually produced in the overall process of iron and steel manufacture. But the other slags that you get from other furnaces may not be as reactive as what you see with the blast furnace. Blast furnace is where you get the highest reactivity because of your calcium addition in the form of limestone. So, again the other slags are overall known as steel slags, okay, because they are produced in the other processes that may come beyond the blast furnace. There are also other slags called ferromanganese slags from other industries, and Linz-Donowitz process slag, LD slag, which is also a type of steel slag, which is posing a large problem for many of the steel companies, because this is not a material that can be used either as cement replacement, because it is not reactive, nor it can be used as an aggregate, because it's got large amount of free lime. What is free lime? Calcium oxide. If you remember, in cement we want to restrict free lime because otherwise it produces unsoundness, it produces expansion upon setting. So, this LD slag tends to have a high amount of free lime, and that makes the use of LD slag even as aggregate quite difficult. Air cooled blast furnace slag, you do not have that problem, but LD slag, the process involves production of the slag which has large amount of free lime. Okay, so, you have to be careful about where the slag is getting collected from and what kind of approach you may have towards utilizing it. Now, so again many of the steel companies have this problem of LD slag and means of disposal. Okay. There is also a different type of iron steel slag that is available called Corex slag. It turns out to be very highly reactive, it is from a direct reduction furnace, and the structure of Corex slag is a lot more finer and a lot more sharp angular texture is shown, which makes it quite reactive as opposed to the regular blast furnace slag. So, as I was saying, LD slag is from a basic oxygen furnace. The process is called the Linz-Donowitz process, and you can imagine the extent of material that we are creating. 150 to 180 kilograms per ton of crude steel is produced. So, 2003 estimates of nearly 1 million ton from Tata Steel alone. Okay, this is the figure from Tata. Okay, 1 million ton per year from Tata Steel alone. So, now this must have grown to probably 4 to 5 million tons, because the capacity of Tata Steel also would have enhanced. As I said, primary problem with this is the high calcium oxide content. Okay. The other aspect is it has got a lot of phosphorus content, and phosphorus content is not very good in terms of your steel corrosion. You want to restrict the phosphorus content significantly. Okay. Now, what people have tried to do is, because it is giving calcium oxide content, you can put this back into the cement clinker manufacture process. It can give a little bit of more lime, but the problem is it is also giving along with lime it will also give silica. So, you have to keep adjusting that calcium silica ratio that comes out of your cement clinker production. Tata Steel has tried to produce aggregate with it. They have various names for it also, Agrito and Nirman, but the problem is again that you have to precondition the material so that the free lime gets converted. What will you do? How can you take care of the free lime before you use it in new concrete? What can you do with the free lime? What is the unsoundness reaction of free lime? Yeah, reaction with water to form calcium hydroxide. So, why don't we have that reaction even before putting this aggregate into concrete, convert as much of the calcium oxide to calcium hydroxide, which upon exposure to environment should convert to calcium carbonate. So, essentially what you are trying to do is mineralize the free lime that is present into a phase that is not going to be affecting the properties of the concrete which is made with the aggregate. So, that is the kind of approach that people are trying to follow before selling this material as an aggregate. Problem still exists that you can't crush easily this material because it's got much higher iron content than even your blast furnace slag, because it's further up in the process than blast furnace. So, more iron content will actually come out with the slag, and it gets harder and harder to crush this material and process it to an aggregate size. Now, very often we talk about industrial processes where we are producing waste which we would like to use as aggregate, because it's a good material as aggregate, it's hard, durable and so on, but that very hardness which makes it suitable as aggregate makes it difficult for the production process of the aggregates. So, you need to crush the aggregate, energy is involved, you need to justify whether the extent of energy that you are putting in to make this aggregate is really giving you the kind of performance that you expect in new concrete. Okay. So, it is not just technical aspects that we need to look at from the performance perspective, the processing and production of the material also are equally important to consider. As engineers, we need to make decisions that are considering all of these aspects together.
So,
yeah.
Since we are adding limestone in this process,
yeah.
won't there be CO2 emission in this process as well?
In the blast furnace slag process, there will still be CO2 emission. Yes, yes, there will be CO2 emission. Some CO2 is going to get evolved. Yes, because in the blast furnace process, you are having temperatures which are high enough, 900 degrees Celsius for instance, where your CO2 can get exited from your CaCO3 that you are adding. Yes.
So, with this slag, it is not sustainable to use.
Well, it depends on what, how this waste gas is utilized. Yes, slag production will also lead to some CO2 formation. Yeah, but see again, what people justify is that you are not producing slag. Slag is an eventuality that happens during the production of pig iron, right. So, this slag that is collected is treated as a waste. So, very often in sustainability analyses, you will see that the amount of CO2 emission or energy for slag removal is not even considered. All of that is attributed to the steel. The CO2 that is getting emitted in this process is attributed to steel, not to the slag. So, you have to remember that this is the production process of steel, not of slag. Slag is collected as a waste. But yes, you have to expend energy, and that expenditure of energy also either electrical energy or whatever to grind the slag to produce the ground granulated slag. That involves significant bit of energy, and the associated CO2 emissions have to be taken into the account of slag when you are actually trying to substitute cement with slag. Okay, again as I said, LD slag has higher phosphorus content, which is not very good for steel corrosion in concrete. Yeah, if you look at current IS 269, what is IS 269? This is standard for Portland cement, yeah, it is standard for Portland cement. Now, there is only one standard. Earlier they used to have different standards for different grades of cement. There is now only one standard, that is IS 269. It allows up to 5% as performance improver, provided you can control the phosphorus content to less than 2%. Okay. And when the same material can LD slag is available to be used as a raw material into clinker manufacture, up to 10% is permissible for that. Okay. So 5% is performance improver. And when is the performance improver added to the Portland cement? After the clinker formation, in the final grinding in the ball mill or vertical roller press, whatever it is, in that process the performance improver is added. So if you are adding this material as a performance improver, right, what is going to happen? The grinding of the slag particles, LD slag particles, is going to be very less as compared to the grinding of cement particles, which are much, or clinker particles, which are much less harder. Here there is a lot of iron present, right. So many phases, iron bearing phases are actually present in the LD slag. So because of this, you have obviously a preferential grinding of clinker that will happen, and slag will not really get ground much. So it may be okay as a performance improver, but again you have to look at the efficiency of grinding.